In this lecture, we're going to study spherical mirrors. There's two types of spherical mirrors we're going to look at. There's the concave mirror and the convex mirror. And they're called spherical mirrors because they are a piece of a sphere. The mirror itself is not a sphere, but it's just a section of the sphere, and one side is mirrored. If it's the inside of the sphere, it would be a concave mirror, and if it's the outside of the sphere that's mirrored, it's a convex mirror. Here's a look at the two types of mirrors. We have a concave mirror and a convex mirror here. You'll see that the concave, the light ray will come in parallel to the principal axis and reflect down. Actually goes right to the focal point. And here we have a light ray going parallel to the principal axis. It reflects upwards. And actually, if you extend this down, it would go down here to the focal point. It's not marked here. But that focal point is halfway in between the center of curvature and the mirror. Now, the center of curvature is also sometimes called the radius of curvature. If you were to make this sphere, if you were to extend this mirror out and make it a big sphere, that C would be right in the center of that sphere, and the focal point is halfway in between that center and the mirror. Here we see an example of that. We have light rays coming parallel to the principal axis. It will reflect through the focal point. This light ray parallel to the principal axis reflects through the focal point. And that's why objects that are very far away, which have light rays that are only parallel to each other when they get to the mirror, will end up being at the focal point. You can also have like spotlights. You can put a spotlight here. The light rays come off of the spotlight, hit the mirror, and bounce straight out. So you can have this reversed as well. Headlamps in a car have this. Flashlights have this. They put the light bulb right here, and behind they have a mirror, and the light goes out, hits the mirror, and goes back outwards. And here it mentions the focal point is half the radius. Here's a picture of a convex mirror. We have this yellow light rays coming in parallel to each other, and you'll see they all reflect right to the focal point. Here's an interesting picture. We have different colors of light coming together, the red, the violet, and the green, all coming in, hitting the concave mirror, and when they intersect right there at that point, they actually make white light. All the colors come together and form white light. At this point, we want to learn how to draw a ray diagram. A ray diagram will allow us to find the location of an image with a drawing instead of an equation. We have to learn the rules of ray diagrams, and we'll do that now. Here we have a concave mirror, focal point, center of curvature. You can see the center of curvature is a distance r away. Focal points r over 2. I'm going to put objects at different points, and we'll see the different rays that can be drawn. I'm going to put an object out beyond C. So here we have our object out beyond C, and there's various rays that we can draw to show where the image is. The first ray we can draw is one that goes out through the focus. What happens is the first ray you draw is parallel to the principal axis, reflects off of the mirror, and goes through the focal point. Another ray you can draw is through the vertex. And if we were to draw that ray through the vertex, that would look something like this. It would come down, hit the principal axis, the angle of incidence would equal the angle of reflection again, and come off at the exact same angle. Where those two light rays intersect would give us where our image is. There's some more lines that you can learn to draw, though. Another line you can draw is from the object through the focus. When it hits the focus, it hits the mirror, and then bounces out parallel to the principal axis. And the last one is if you go through the center. And if you go through the center, it looks something like this. The light ray goes through the center, hits the mirror perpendicularly, and it bounces right back through the center again. You can use any two of these light rays to find out where your image is, or you can use all of them, and I'll show you how that works. If we use all of them, it looks like this, and where they all intersect right there is where your image is formed. So you don't only have to draw two of those. Like typically I would draw the red one and the blue one together and come up with this point, but you can draw all points. So I suggest you practice drawing these ray diagrams. We'll go ahead and put our object at different places to show the different ray diagrams. We'll go ahead and put our object here at the center of curvature, and we'll draw our first ray. Goes parallel to the principal axis and ends up through the focal point. We can do all the other ones as well. Through the vertex, draw that ray. Through the focus, if you want to draw that one, it'll come out parallel to the principal axis. And we can't draw it through the center because we're on top of the center. So let's just show all the rays. And you'll see in this case they only had 3 rays, but they all intersect right at C. So if you have an object at C, the image is at C as well. It's inverted and it is real. Because it's inverted, it's a real image. The previous one was a real image also. Here I want to show an optics bench, this is called. I'm able to grab the object and move it around. And this right here is where all the light rays intersect, and that's called the image. And you can see that I am moving it back and forth. And you can tell right there, that's the center of curvature. I put the object right at the center of curvature because the image is right at the center of curvature as well. And then I push it out, and you can see it gets larger. So there's a pattern here. If you're out beyond the center of curvature, if your object is out there, your image is smaller and inverted, which means it's real. And as you get closer and closer, it stays real because it stays inverted. It can be projected onto a screen. And here you go in between F and the center of curvature. You can see that your image gets very large. And right when you hit the focal point, you get no image at all because these light rays coming off are parallel to each other. So there's no intersection. And then when you move in closer, you can see that a virtual image forms inside the mirror. It's a large virtual image. So now I'm going to draw some ray diagrams for different situations. This first situation is our object here is out beyond C, so I'm going to look at this one here. And what I do is my first light ray I draw is parallel to the principal axis. And this light ray is coming off the object. And what I'm going to do is it reflects through the focal point. And then my second one I always like to draw is the one that hits the vertex. So I draw it, comes down, hits the vertex, bounces off, angle of incidence equals angle of reflection, and my image ends up forming right here, like that. And the image itself ends up being real because it is inverted, and it ends up being smaller than the object. Now if I put my object right at C, that's this one right down here, I draw my light ray parallel to the principal axis. Once again, it goes right through the focal point. I draw it down to the vertex, hit the vertex, reflect back, angle of incidence equals angle of reflection. You'll see I hit right there at the position C, and so this is my image. And in that case, the image, again, is real because it is inverted, and it is the same size as the object. If I go ahead and I'm going to put my object right at F, and I'll do that right here. Actually, I'm going to put my object between C and F. I'm going to put my object right here. Here's between C and F. So here's my object. We're not going to worry about this object out here. It'll be out there. I draw my light rays parallel to the principal axis, reflects through the focal point, and then I draw it down to the vertex, reflects off the vertex, angle of incidence equals angle of reflection, and it intersects somewhere out there beyond the center of curvature. So my image actually is right there. And in that case, let me erase this out of the way. In that case, that image that's formed right here it's still real because it's inverted, but now it's larger than the object. Now if I put my object right at the focal point, let me go ahead and do that. I'll erase this here. I'm going to put my object right at the focal point, right there. What will happen is I'm going to end up with no image because all the light rays that come off of this object are parallel to each other. So I draw it parallel to the principal axis, goes through the focal point, draw it down to the vertex, comes off parallel, and they don't intersect. They're all parallel. So here, there is no image. Now, if my object is in between the focal point and the mirror, I draw my ray, I draw my parallel to the principal axis ray, goes through the focal point. I draw my vertex ray, and look, they diverge on this side. So I have to go back through the lens and find out where they intersect, and they intersect right there. And here's my image is formed. And in this case, the image is virtual because it's right side up. All virtual images are right side up, and it is always larger than the object. Now, convex mirrors are a little bit easier. Their ray diagram is pretty simple, and I have 3 different situations, but they're actually all the same. The ray diagram, you draw a parallel to the principal axis, and it reflects off up here, but it has to reflect in line with the focal point. And then my other light ray comes down right to the vertex again. Angle of incidence equals angle of reflection. These two are diverging away from each other, so you have to follow them back through the mirror, and my image ends up being right there. So the image is always virtual and always smaller. It's virtual because it's upright. And if I did the exact same ray diagram over here, parallel to the principal axis, you have to line it up with the focal point when it reflects off. The light ray comes down, hits the vertex, bounces off. Angle of incidence equals angle of reflection. These two are diverging, so I have to follow it back through, and then my image forms here. So it doesn't matter for a convex mirror, the ray diagram will always be the same. Now this is kind of an interesting apple. You have a ray diagram here, and we're out beyond the center of curvature. But if we were to take our object and move it right there, you know you're right at the center of curvature. And then you move it in closer, and it goes out beyond. When you're between the center of curvature and the focal point, it goes out beyond. When you hit the focal point, no image. When you come in closer, there's your virtual image. Do the same thing for a convex mirror, but you'll see that the image is always on the right-hand side, always upright, always virtual. Doesn't matter where I put my object, these light rays that are bouncing off will always intersect on the other side. Now, instead of drawing ray diagrams, we can now use equations as well to find out where our object and image is. 1 over DO plus 1 over DI equals 1 over F is an equation. DO is the object distance, DI is the image distance, and F is the focal length. So looking at this picture, we see that object distance is the distance from the object out to the mirror. That's this right here. Image distance is from the image to the mirror. That's this here. And there's other variables here. The height of the image is this height there. And the height of the object is this height here. The last variable we have to know is the focal length. That's from the focal point to the mirror. That's our focal length. And now we can use all these variables with our equations to solve our various physics problems, to calculate where the image distance is or the object distance is, etc. So once again, here are our equations. Like I mentioned, the 1 over DO plus 1 over DI equals 1 over F. The H over HI equals D over DI. That's actually the magnification equation. And actually, this itself, magnification equation, actually is more this. It's magnification is the height of the image compared to the height of the object, which is equal to DI over DO. So you'll see it written both ways. When you want to talk about magnification, you want to know how tall is the image compared to the object. And you'll also see this negative sign in front of it. Although I don't worry too much about the negative sign, it's just an extra thing that we don't need. All we really want to know is how much is it magnified by. That's a comparison of height of image to height of object. Now the last thing we have to know is there's some rules that we have to follow. F is positive for a concave mirror. That's this first rule up here. So and F is negative for a convex mirror. Now we have other rules here. DO is positive always, so that occurs all the time. And DI is positive if the image is a real image, and DI is negative if it's a virtual image. Now with these rules, we can go ahead and approach our physics problems. If you would like to see some examples of some problems being solved, you can look at the videos of the homework that I've done online as well. So this concludes our video for this section.